This is going to be a lesson on right triangle ratios. The goal of this lesson is to be able to find the lengths of a right angle triangle's sides with respect to its angles. In order to do this, we're going to need to study the effects of growing or shrinking a triangle on its side lengths. To begin with, I've drawn on some random triangle whose base is 3 units wide. And the left side over here is exactly 45 degrees to the base. We'd like to figure out what happens to the lengths of these sides as we scale up the triangle. Now, we've scaled this triangle up so that its base is twice as large as it was when we started. We'd like to figure out whether the other sides have also increased by a similar proportion or not. If you look carefully, you'll notice that this smaller triangle takes up 2 diagonals, and this larger triangle takes up exactly 4 diagonals. So it turns out that this has also doubled in size. Similarly, if you look at this side over here, you notice that we go up by 2 and then left by 1. And in this case, we go up by 4 and left by 2. This means that this has also doubled in size. Now what we notice is that when we scale a triangle by a factor of 2, we also scale all of the sides by the exact same factor. So let me go ahead and rename these 3 sides to capital A, capital B, and capital C to indicate that they've been scaled. Now, this allows us to write the fact that if we scale the triangle by a factor of 2, this capital A will be equal to 2 times this little a, and the same goes for B and C. Now, without changing the picture, I hope you realize that there's nothing really special about scaling it by a factor of 2. We really could have used any number, so I'm going to go ahead and replace any reference to 2 for a scale factor s. Now these equations aren't saying anything complicated. For example, this side used to be 3 units wide, and now, after the scale up, it's 6 units wide because we scaled up by a factor of 2. Now we can actually use this idea on sine and cosine to scale the unit circle up to any size that we like, which I'll show on the next page. Let me start by drawing the unit circle in the first quadrant. Now if we go ahead and select a random angle again, and then project a ray out to the unit circle, we know that the x-coordinate is cosine and the y-coordinate is sine, as we've said before. Now for this lesson, we're actually going to visualize the cosine and sine a little bit differently. Instead of drawing the arc of the circle, we're going to draw a little triangle beneath the circle. Now of course, since the x-coordinate is the same thing as cosine, then the distance from here to here is just the same thing as the cosine of theta. And similarly, since the y-coordinate is just the same thing as sine theta, then the height from here to here is also the sine of theta. Now since this is just the unit circle, and this is just the radius of that circle, then the length from here to here is just equal to 1. Now it turns out that we don't actually need any of this information anymore, because it's already marked on the triangle below, so let me just get rid of it. Now since this 1 is just the hypotenuse of this triangle, I want you to imagine that we scaled this triangle up so that it had a new hypotenuse. Now since this is a larger triangle, it follows that this length over here is going to be the radius of a new, larger circle. Now since this is the hypotenuse of our new, larger triangle, we're going to go ahead and label it with a capital H. Now since this side over here is adjacent to our angle, we call it the adjacent side and label it with a capital A. And now finally, since this side over here is opposite to our angle, we call it the opposite side and label it with a capital O. Now in this particular triangle, it's easier to figure out how much we've scaled the triangle up by. Since this was 1 and this is h, we must have scaled the triangle up by whatever this number h is. So we've just written that we've scaled this unit triangle into this larger triangle by using a scale factor of h. And therefore that if we took this cosine theta and multiplied it by h, we would just get this a over here. So this length a is given by h times the cosine of theta. Now similarly, we also have to scale this sine theta up to get to o. So that means o is given by h times the sine of theta. Now since we said that the tan of theta is just the sine of theta divided by the cosine of theta, we can go ahead and divide this equation by this equation to get one final equation for the tan of theta. So this immediately tells us that the tan of theta is equal to the opposite side divided by the adjacent side's length. Now I'm just going to write this in a way that's a little bit more similar to the way it's usually taught. So first I'm going to go ahead and divide both sides of this equation by h. So if we pull this h to the bottom of this equation and we swap the two sides, we'll just get this expression. Now I'm going to do the exact same thing for this expression. So we did the same thing here. We just divided this h to the bottom of this o and we swapped the two sides to get this. Now finally, I'll just go ahead and swap the two sides of this equation as well and get rid of these three equations on the left. Now it's very likely that you're going to use these equations so much that I have this useful mnemonic that pretty much everybody learns when they see these the first time. So the mnemonic is SO, KA, TOA. Since the sine of theta is just the opposite over the hypotenuse, we write it as SO. Since the cosine is just the adjacent over the hypotenuse, we write it as KA. And since the tangent is just the opposite over the adjacent, we write it as TOA. Now I'm a really visual learner, in case you couldn't tell by now, so I usually remember it with these three little pictures instead. Now in my head, we bounce sine off the back wall and to the hypotenuse. For cosine, we bounce it on the floor and hit the hypotenuse, and for tan, we bounce it off the back wall and hit the floor. Now just a word of warning. Throughout this whole derivation, we've assumed that the triangle we're working with has a right angle. This means that SOHCAHTOA only works when you have a right angle. If your triangle doesn't have any right angles in it, you just shouldn't use SOHCAHTOA. We'll show you what to do with those triangles in a later lesson. Now you're going to very frequently use SOHCAHTOA to find missing sides and angles on right angle triangles. So I should give you some examples of that first. Suppose for a moment you're standing in front of the tallest building in the world, and you're trying to figure out how tall it is. So you decide to walk away from it for some distance. So what you do is you open up the compass on your phone, then point it at the ground of the building, and then tilt it so that it's pointing directly at the top of the building. And you find that the angle between these two extremes is 70.08 degrees. So you're trying to find the opposite side, and you do have the adjacent side. You don't really care what the hypotenuse is in this case, so we use the tan of theta. If we then go ahead and multiply both sides by 300, we'll be able to actually find the value of x. Now this immediately shows you how we could use SOHCAHTOA to find missing sides, but we can also use it to find missing angles. So let me put on another problem for a moment. Now this time you're on a soccer pitch. That's right, a soccer pitch. And you know its length is 100 meters. Suppose you had some kind of measuring device, and you measured the diagonal of the soccer pitch to be exactly 120 meters. This time you'd like to know what the angle between the edge of the soccer pitch is to the other diagonal, so you can work that one out too. Now this time you can see that the adjacent and the hypotenuse are involved, so you're going to have to use the cosine of theta this time. This time, if we take the arc cos or cos inverse of both sides, we're going to get the following result. As we said in an earlier lesson, cos and the inverse of cos are undo buttons of each other, and you can cross them out when you know that your angle is going to be less than 90 degrees, which in this case, because you have a triangle, it has to be. Just a quick reminder, some calculators don't actually allow you to type in acos. In those calculators, you'll probably have to use this symbol instead. So you'll just have to use a different symbol based on which calculator you have. And with this, we've completed our examples. And now, with this information, we've completed our lesson on the right-angled ratios. You can use SO, KA, and TOA to solve for missing angles or side on any right-angled triangle.